This is a walkthrough of a higher GCSE Chemistry paper for AQA, and this is for paper 1 and it's from May 2024. So let's start with the first question. Copper is a useful metal. Figure 1 shows the mass of copper produced between 1900 and 2010, and it says give 2 conclusions that can be made from figure 1. Now the most obvious conclusion, you can see the shape of the graph, it's going up. So that means something must be increasing. What is increasing? Just look at the axes. The mass of copper produced each year is increasing. So that is going to be our first answer. And then so I've just written there the mass of copper produced each year increases. And then the other thing for the second mark is that you should notice that it's not a completely straight line. So the increase isn't a constant. And you can see that towards the beginning between 1900 to about 1925, the increase is there, but it's much slower. So that will be your second mark. So there you go, between 1900 and 1925, the rate of increase is slower. Now let's move on to the next question. This is about alloys. And now what you have here is the pure copper metal, and you can see that the atoms are all the same size and they're all in beautiful straight lines. And these layers allow give the metals the property of being ductile and malleable because they can be hammered into shape. The layers can slip over each other, and you can even draw them out into wires. However, the alloy is not in uniform layers. And you can see that the atoms are different sizes, and that's why it's not in uniform layers. So this is worth 3 marks. For the first mark, I would actually say what I see. So describe that diagram. So there you go. I've written there, in the alloy, the atoms are different sizes. And then you have to talk about a consequence of that feature. So I've written there, as a result, the structure's layers are distorted. And then finally, you have to say, relate that back to the question, why does it make it harder? And there you go. This means that the layers cannot slide over each other, making it harder. Moving on to the next question, which is 1.3. So this is really a maths question. And what you're doing, you're looking at a 5.25 gram sample of an alloy of copper. So we start off with 5.25 grams. And that is a mixture of copper and zinc. But it tells you that the zinc is 13.5%. So you have to work out what the copper is. So that must be 100 minus 13.5%. And that comes up to 86.5% is the copper. And it's asking you not what the percentage is, but what percentage it is as a mass. So you want the answer in grams. So all you do now, you just work out 86.5% of 5.25. So if you want to do that in a calculator, that's 86.5 divided by 100 multiplied by 5.25. And we get 4.54 grams, and that's your answer. Question 2 is about making a soluble salt, and what you're doing, you're taking copper carbonate and you're adding it into a beaker which has some acid in it. So these sort of questions, I always make sure that I understand what's going on, and usually some diagrams are given. And the first question is a simple multiple choice. What is the formula of the acid used to prepare copper sulfate? Well, at the beginning we had copper carbonate, reacted it with the acid, and we ended up with copper sulfate. Well, here is the clue. Sulfate must have come from the acid, and the only acid which has got sulfate in it is this one, and the answer is H2SO4. Now let's go on to the next part. Why is excess copper carbonate used in stage 1? Now, if you look back at the diagram, you add the copper carbonate, which is a powder, and you can see that it's an excess because look, you've got some unreacted copper carbonate left in the beaker. And the reason why we add an extra amount of copper carbonate is because we want to make sure that all of that acid has reacted. So that's what I'm going to be writing here. So there you go, so that all of the acid reacts. And then going on to 2.3. Beaker N contained copper sulfate. Describe how the student could produce copper sulfate crystals from the copper sulfate solution in beaker N. So let me show you beaker N again. So that's the beaker and it's got copper sulfate solution. Copper sulfate solution is a mixture of copper sulfate crystals and they are dissolved in water. So we have to get rid of the water, don't we? So to remove the water, what you need to do is you need to heat it. So that is going to be my first comment. Heat it to evaporate most of the water. And then you want to leave it to cool and evaporates more slowly to give crystals. Oops. So that's your next question done. Moving on now to 2.4. A student investigated the thermal decomposition of copper carbonate. So what you do, you take some copper carbonate and you heat it in a test tube. And copper carbonate decomposes to form two products. And this is the method that they used. So you add the copper carbonate into the test tube. Again, take a little while if you're doing this. Take some time to actually look at that diagram, look at the instructions, and almost pretend that you're actually doing this yourself. You heat the test tube and the contents until the mass does not change. Record the mass of the contents of the test tube after heating. Repeat steps 1 to 3 with different masses of copper carbonate. Okay, so here is the table of the results. And I'm going to move on because I knew that was going to happen. It says plot the data from table 1 on figure 5. So I'm going to do that now. So I plotted the graph, and I didn't have a ruler. It was difficult for me to do it with a ruler on the screen, but this is what it should look like. The line of best fit should go through 0 ideally and through as many of the points as possible. And then the next question is, why does the mass of the contents of the test tube decrease in mass when copper carbonate is thermally decomposed? Well, it's decreasing means that something is escaping, and I'm going to say because it decomposes to make carbon dioxide gas, which escapes. Okay, so you are expected to know that carbonates decompose to give carbon dioxide. The clue is in the name, carbonate, carbon dioxide. Okay, now the next part of the question, this is going on to question 3 now. A 6-mark question on structure and bonding, and we're comparing two structures. So you've got sodium chloride, and you've got the diagram there, and then you've got oxygen. And it says compare the structure and bonding of sodium chloride and oxygen. My approach here would be to do 2 paragraphs. So let's start with sodium chloride. Now be careful when you're comparing. You want to put in similarities and differences between the two. So let's start with sodium chloride first. So the first thing I noticed there is that sodium chloride is made up of positive and negative ions in a giant ionic lattice. And then the next thing I'm going to say about sodium chloride is that NaCl has ionic bonds. So that's my first bullet point. That's my second bullet point. What else can I say about it? I can also say that NaCl consists of ions with full outer shells. And then I'm going to look at a difference. NaCl is a compound because it's made up of 2 different things joined together. You can also say here that it consists of ions with full outer shells. It's an ionic bond made by electron transfer. You can say that as well. Now let's talk about the oxygen. So I want to do a different paragraph for oxygen. So you've got the diagram there for oxygen. That's a molecule. So that's the first thing I'm going to say. Oxygen exists as molecules with, and you talk about the bonding here, with strong, not ionic but covalent bonds between the atoms. You can say there's a double bond if you wish to. Okay, the next thing I'm going to say, electrons are shared between the oxygen atoms, and then the next thing I'm going to say is, which is a difference, I'm going to say oxygen is an element. So that should be enough to give me my 6 marks. Now let's move on to question 4. Nitric acid is a strong acid. What is meant by a strong acid? Okay, so I want you to learn this as a definition. Learn the definition of a strong acid. It's something that is fully ionized or fully dissociated in solution. So there you go. Next part is nitric acid is used as a dilute aqueous solution. What is meant by dilute aqueous solution? Dilute means we've just added water to it. So there you go. It's different to a strong acid. So weak acids can also be dilute if we add water to them. Okay, moving on to the next part, 4.3. So this is talking about changes in pH. So we start with pH 1 and then we add water. And then when we add water to the nitric acid, it changes to pH 3. So that means that this acid has become a weaker acid. So a weaker acid means it's got less H plus ions in solution. Okay, how much less? Well, every time you jump 1 pH, that is a factor of 10. But we've jumped 2 pHs, so that means it must decrease by a factor of 100. And then write the ionic equation for the reaction between an acid and an alkali. This is for any acid. Acids are always represented by H+, so that could be nitric acid, it could be sulfuric acid, it could even be copper carbonate, which we saw earlier on this paper. And then any alkali is usually OH-, and they react together to form H2O, and that is your equation for any neutralization. Okay. Now moving on to the next part. So it's asking you to state what the molar ratio is for the number of moles of magnesium carbonate. Let's find magnesium carbonate. There is magnesium carbonate. And the number of moles of nitric acid. There is nitric acid. Now, if you look here, there is an invisible 1 there, but we just don't write it in. So we've got 1 mole of magnesium carbonate. So I can eliminate that and eliminate that because they start with 2. But the number of moles of nitric acid, there is a number 2 there. So this is your correct answer. Okay, next question. So quite a few students, when I was looking at the examiner's report for this, actually got caught out with this because they didn't read it properly. So we always assume it's neutralization, so the pH is going to be neutral pH, which is green. But the important wording here, a student mixed some magnesium carbonate with an excess of nitric acid. Excess means we added extra, so there will be some acid left over. If there is acid left over, then the color is going to be red. Okay, let's move on to the next part. A student investigated the temperature change when different masses of magnesium carbonate were reacted with excess nitric acid. So again, as with these type of questions, I want you to look at the diagram carefully and pretend that you're doing this experiment yourself in the laboratory. So you start off with 0.5 grams of magnesium carbonate powder. Okay, and in the beaker, in the cup there, polystyrene cup for insulation, you're adding nitric acid. So you've got your nitric acid in there. You put a thermometer in there to take the temperature, and then you measure the temperature of the solution first. So the temperature at the start, then you add your magnesium carbonate, add 0.5 grams of magnesium carbonate, and then you stir the mixture, usually with a thermometer, and then you measure the temperature. It doesn't tell you when to measure the temperature, but I would say you would measure the temperature at the end, or measure the temperature when it stops increasing. So mark the point where it stops increasing, but we'll see. And then it says repeat steps 1 to 5 with different masses of magnesium carbonate. So you could use 0.5, 1, 1.5, 2, etc. So the question is asking, give 2 improvements to the method to produce more accurate results? Well, always when it comes to accuracy, it says do not refer to the improvements in the apparatus in your answer. So I can't say put a lid on the beaker. That would be better as well. So always when it comes to accuracy, we have to do repeat measurements. But I can see that in the instructions here, we only did it once with 0.5 grams. So the first thing I would say is I would repeat the measurements with 0.5 grams at least 3 times and then work out the mean. So that's what I've written there. Repeat the experiment 3 times with 0.5 grams and work out the mean. So you must mention working out the mean, otherwise you're not going to be awarded that mark. And then the second thing I would do is I would measure the highest temperature that's recorded, because it says here measure the temperature, but it doesn't tell you when to measure it. So you measure the highest temperature recorded. So that would be my second point. And there you go. That's my answer for this question. And now we're going to move on to, there's no question on there, on to the next question. So this question is about ammonia, actually NH3. And you're given the electron shells for ammonia, and it says to complete the dot and cross diagram for an ammonia molecule. Now, really what you need to know here is how many electrons there are in the outer shell in the nitrogen and each of the hydrogens. Now if you look at your periodic table, nitrogen has 5 electrons in its outer shell because it's in group 5 of the periodic table, and hydrogen is not really in any group because it's on its own in the middle of the periodic table, but that only has 1 electron anyway, so that will have 1 electron in its outer shell. Now you can use different colors or you can do dots and crosses. I prefer to use dots and crosses. So what I'm going to do, I'm going to draw the 5 electrons for the nitrogen. The easiest way to do this is to do them in the overlaps first. So you do 1, 2, 3. Okay, those must be in the overlap, and then the other 2 must not be in the overlapping regions. And then you're going to put in the electrons for the hydrogens. Now each hydrogen has 1 electron, so you do 1 cross for each of them like that, and then you just do a quick count: 2, 4, 6, 8, full outer shell. And then hydrogen can only have 2 in its outer shell because it's only got 1 shell, so both elements have full outer shells, and that's your answer. Now the next question, this is a mole calculation question, and it says to calculate the mass of hydrogen that is needed to produce 25 grams of oxygen. So with all of my mole calculation questions, I actually write down all of the information here inside somewhere near the equation. So 25 grams of ammonia, let's find it in the equation. There it is, and I'm just going to write here 25 grams. And then it says calculate the mass of hydrogen. Let's find hydrogen there, and that's where I want to go. Okay, so it's important to do this because it means that we only talk about the hydrogen and the ammonia. We can ignore the nitrogen. We don't need to do anything with that at all. So I'm just going to cross it out just to make it easier. Now, as with all calculations with moles, for GCSE Chemistry, you will not be given the moles formula, so you have to memorize it. So I'm just going to write it here on the side. So moles equals the mass divided by the MR, or the relative atomic mass. Okay, and then if you want to, you can do the triangle as well. So there's my triangle. N is moles. That's a symbol for moles that we use in chemistry. So moles equals mass over mR. So have both of them if you're not sure, but this is something you have to memorize. Now, whenever I do mole calculations, I always teach my students 3 steps. Step 1 is always moles. Now, what do I work out the moles of? There's only one thing you can work out the moles of, and that is the moles of ammonia, because we know we've got 25 grams of ammonia. So I'm going to write moles of NH3 equals mass over the MR. And the mass is 25, and the MR is these numbers here added up. Ammonia is 1 nitrogen, so it's 14, plus 3 hydrogens. 14 plus 3 is 17. Actually, I'm going to do it here, and that gives you 1.47 moles. Okay, now step 2 in all my mole calculations, and this, by the way, is the step that most students miss out. Step 2 is your molar ratios. Okay, it's your ratio step. Now, what are we talking about? This is why I put this here at the beginning, because it means that you're not talking about the nitrogen, you're talking about these two things. So we're just going to copy these exactly how they are in the equation. So you've got 3H2. So I'm going to write it here, 3H2, but now I'm going to do a ratio sign and then 2NH3. Oops. Now this number 1.47, that was the number of moles of ammonia. So I'm going to write here 1.47. So 1.47 is the same, is in the ratio with a hydrogen in a 3:2 ratio. So what I do to 1.47, I divide it by 2 to get 1 and then times it by 3. So then that will give me, I got 2.205, and then finally step 3. Step 3 is what I'm trying to work out, and this is the question mark. Go back to the question, calculate the mass. So I'm going to work out the mass, and it's important to write down the mass of which substance. So mass of H2. Okay, so we use this triangle, mass equals moles times MR. So it's N times MR. And the moles is that number that I get from step 2. So it's 2.205 times the MR. The MR is the mass of hydrogen, and that's going to be 2 because it's 1 times 2, which is 2. And then I get 4.41 grams, and that's your answer. Okay, now moving on now to the next part. This question, I'm going to go through this quite slowly, of bond energy calculations, and it's a grade 7 to 9 topic, so it can be quite tricky. So I'm going to try and simplify it as much as possible. In this question, you are given the equation, but you are also given, it's not just a simple question of working out the bonds made and working out the bonds broken and then looking at the difference, because you're actually working out the bond enthalpy of one of the reactants, which is the hydrogen to hydrogen bond. Okay, so the first thing it tells you here is that the enthalpy change, okay, the energy released forming new bonds is greater than the energy needed to break bonds. Now, one thing you need to remember, the bonds on this side are the bonds which are made. So bond making is a negative process. It's an exothermic process. Here are the bonds which are broken. And this is an endothermic process because you need to absorb energy to break bonds, endothermic process. So it's going to be positive. So that's the first thing you have to remember. So what I'm going to do, just for a simplicity's sake, there's not much room here. You're also given a table of bond energies, but I'm just going to write that equation out again so that we can do our calculations. So this is what I tend to use. So the energy change, the total energy change in a reaction is the sum of the bonds broken, the energy of the bonds broken, and the energy of the bonds made. So which bonds were broken? So we're going to have a look back here again. The bonds that were broken was one of these, which is a nitrogen to nitrogen triple bond, and that was 945 kilojoules per mole. So I'm just going to actually write them here. So we broke a nitrogen to nitrogen triple bond, and then we also broke 3 hydrogen bonds. Okay, so that's your bonds broken, plus the bonds that were made. If you look back at the equation, we made 3 nitrogen to hydrogen bonds, but there's 2 of them, so we made 6 NH bonds. So I'm just going to write here 6 nitrogen to hydrogen bonds. So these are the bonds which were made. Now we have to put our numbers in. So the energy change, they give it to you here. It says it's 93 kilojoules, but because it's formed from releasing, it's the energy which is released. Okay, energy release is an exothermic process, so it's negative. Even though it says positive 93 there, we have to make it minus 93. And then that equals the nitrogen to nitrogen triple bond, which is 945, plus the 3 hydrogens, which we don't know, plus the 6 NH bonds. So that's 391 times 6, which comes up to 2, 3, 4, 6. But the other thing you have to remember is that this process, because we're forming these, we're making these bonds, it's a negative process. So that actually is not plus 2396. That becomes a plus and a minus there. Now it's just a simple problem of rearranging this so that you've got 3H2 left on its own. So when you do that, you get 1308 equals 3H2. So that's the bond enthalpy to break 3 hydrogen to hydrogen bonds. You divide that by 3, and therefore you get, so if you just divide it by 3, you get 436 kilojoules per mole. On to the next part. Energy is released from the reaction to produce ammonia, and we have to draw an energy profile diagram and a reaction profile diagram. So with reaction profile diagrams, we know its energy is released, which means that it is an exothermic reaction. So in an exothermic reaction, I would just memorize this. Okay, so we put the reactants here. So you've got nitrogen plus 3 hydrogens, and the products will always be further along and at a lower level. So you're making 2 NH3, and that's your products. So if you want to, you can write here reactants and you can write here products. Okay, the next thing you have to do is you have to do your line, sort of like it goes up a mountain and it goes down here. And then it also asks you to clearly label, complete the profile line, label the energy level of the reactants and the products, and label the overall energy change. So the overall energy change is the difference in the level of the reactants and the products. It goes down because energy is released. It's exothermic, so it must be going down. And then I'm just going to write here energy change, and that is your 3 marks for that question. Okay, now moving on to the next question. In the earth, most metals are found as compounds. Name one metal that is found in the earth as the metal itself. That's quite straightforward. It is gold, because gold is unreactive, and you know this from gold mining and things like that. Okay, the next one. Suggest the most economical method for extracting metal Z from an oxide of metal Z. Well, what you should notice here from the reactivity series, we see that carbon is more reactive than metal Z. So this means that carbon can displace metal Z from its oxide. So I would just say react it with carbon so that Z is displaced or kicked out from its oxide, or the carbon reduces it. You can say that as well. Okay, next question. So here you've got the electrolysis of aluminium from aluminium oxide. Now what you do is you pour molten aluminium oxide. You have to have it molten, otherwise it doesn't conduct electricity because it's an ionic compound. Once it's molten, the problem is that the melting point is really, really high, something like 3000 and something. And that can make electrolysis very expensive. So we add a substance to the mixture of the molten aluminium oxide to lower its melting point. And you need to know the name of this substance. This substance is called cryolite, and it just lowers the melting point and makes the whole process cheaper and quicker. And then explain what happens to the positive carbon electrodes during the extraction of aluminium from aluminium oxide. So I'll just do a bit of an explanation here. Aluminium oxide, when you pass electricity through it, it splits and you get aluminium metal, okay, which you collect and you pour it off, and then you get oxygen, and oxygen is a gas. So the first thing that happens is oxygen gas forms and it reacts. So this is your second mark, reacts with the carbon electrodes. And because it reacts with the carbon electrodes, those carbon electrodes start to wear away, gently wear away. So they have to be constantly there. You have to renew and replace those carbon electrodes. So there you go. So they wear away and have to be replaced, and that will give you your 3 marks. And then the formula of aluminium oxide is Al2O3. Now you should know this, especially if you're doing the higher paper. You can use a periodic table as well, but aluminium is in group 3. So this means it has 3 electrons in its outer shell, so it forms Al3 plus ions. So in aluminium oxide, when it's molten, you have aluminium ions floating around, and these are the ones which will float off to the negative electrode, and they will go to the negative electrode and they will pick up 3 electrons, and then once they've picked up 3 electrons, they just become pure aluminium metal. Okay, now let's move on to the next question. Halogens are elements in group 7 of the periodic table. Calcium reacts with chlorine to produce calcium chloride. Explain what happens to calcium atoms and to chlorine atoms when calcium reacts with chlorine to produce calcium chloride. So basically you're explaining how they join together. So they join together by forming ionic bonds. So the first thing I would probably explain is what happens to the calcium. So calcium has 2 electrons in its outer shell because it's in group 2, and it loses those 2 electrons. Once it's lost those 2 electrons, the calcium atom is not a calcium atom anymore. It is now a calcium ion with a charge of 2+. Now what happens to the chlorine? Now chlorine is in group 7. So they have 7 electrons in their outer shell. They only need 1 more electron, but you've got 2 electrons which has been donated by the calcium. So that means that for each calcium you need to have 2 chlorine atoms to accept those 2 electrons. So I've written there, chlorine has 7 electrons in its outer shell and needs 1 electron to get a full outer shell. How does it do that? So we need 2 chlorine atoms for each calcium, and I'm just going to put in the 5th point, each chlorine becomes Cl minus. Okay, and then if you want to, you can write the formula for calcium chloride is CaCl2. It asks you to explain why chlorine is more reactive than bromine. So this is worth 4 marks. The first thing I would say is to compare them. So firstly, chlorine is smaller than bromine. There you go. So what does this mean? This means that the outer electron shell is closer to the nucleus. So the attraction for the incoming electron, because chlorine has to and bromine have to accept an electron, is greater. And so chlorine gains electrons much more easily. So there you go, chlorine gains electrons much more easily, and that is your 4 marks. Moving on to the next part. So part 7.3, you're given the boiling points of 4 hydrogen halides, and it says describe how the boiling points of the hydrogen halides change as the relative formula mass changes. Most students got 1 mark out of 2 on this. And now the easy mark is here. If you look at the trend, you're looking for a pattern. So we're going down the group. As you go down the group, okay, the boiling point increases. So that would be your first mark. So there you go. As you go down the group, and you have to specify from HCl to hydrogen iodide, the boiling point increases. Now to get your second mark, you have to realize that hydrogen fluoride does not follow the same pattern. So that's what I've written. You can also say that hydrogen fluoride is higher than expected. Okay, moving on to question 8. This is on nanotubes. Describe the arrangement of carbon atoms in the nanotube shown. So each of these corners is a carbon atom. So it's a single layer of carbon atoms where each carbon is arranged in hexagons. So I'm just going to write that now. So carbon atoms in a single layer or singular layer in hexagonal rings. Nanotubes are used in electronics. Give one other use of nanotubes. I'm going to say drug delivery. There are other uses. Another common one is cosmetics, sun creams and things like that. Cosmetics and also sports equipment. because they're lightweight and they are strong. So any of those three are the most common ones. Okay, this next question is a calculation question and it uses Avogadro's number. So it's just a simple ratio question actually, because 6.02 times 10 to the 23 is 1 mole. And that's how many particles you've got. We don't have 6.02 times 10 to the 23 particles. We have only got 2380. So what it's asking you is how many moles is that? So you just do this. You just do 2380 divided by Avogadro's number. Okay, and the answer is 3.95 times 10 to the minus 21 moles. Okay, now question 4 is 3 marks, 8.4. Explain why carbon nanotubes can conduct electricity. So refer to bonding between carbon atoms in your answer. So point 1, each carbon, so I'm just going to describe the bonding in the carbon. Each carbon is covalently bonded to 3 other carbons. So it's bonded to 3 other carbons. The final electron is not bonded to anything, so it is delocalized. So the 4th electron is delocalized and free to move, and then relate it back to the question, so they can carry the current, can carry the charge. And therefore that's why they conduct electricity. And that's the end of the paper.